Yeah, so theory of gyroscope. Gyroscope. I don't know if you saw gyroscopes, probably you saw some of those objects, or better to say instruments. So what it is, it would be certain wheel. Probably let me put on the screen first, so you can see those devices. So it would be a certain wheel rotated on axle, and then if you place that axle on certain pivot point, then that wheel would perform, in addition to its own rotational motion, would perform additional, rotational motion about its axis. It would also participate in rotational motion about certain axis. Yeah. You see those gyroscopes here. So let's discuss a little bit theory first. But let's say you have a wheel which rotates, kind of you gave a certain rotation, so that wheel would have then angular momentum, as we discussed, depending on frequency of rotation or its angular velocity. So it has omega. Now let's show a certain system of coordinates. So let's say that is our pivot point. Here's certain axle of that rotating wheel, and we can locate it on that pivot point. Let's show O here. Let's show distance r from that pivot point, position vector, to center of mass of that wheel, which would be center of it. What forces would be acting on that wheel? Would be weight. Let's show W, which is mg. Given that m it is mass of the wheel, because that force of gravity would give certain torque. So what we have torque. We remember tau. It is always position vector multiplied by force acting by W, right? So if you look at that picture, so R is acting to the right, W downward. So we can kind of like take that vector and place it into that point. So it will be easier to find the result of cross product. So here, if you wish, we can show that position vector R, because was said many times, we can transport vector to parallel to itself. So from R to W we rotate, right hand rule, for example, or right-handed screw rule. So torque goes into the whiteboard, so we can show like a small cross. I can show the torque over here, because again it is vector, I can transport anywhere I want. So tau goes into the whiteboard. A result of cross product, again. So that torque would give additional angular momentum to existing already. So let's show that addition like dl. And as a result, our wheel will get a little bit different position. So it will rotate in a moment in the film. Writing. That wheel will get different position. So it will start to rotate in plane which is perpendicular to W, or in plane of radius vector r. So it would perform rotation like that. Thus, we would have so-called angular velocity of precession. So a phenomenon is called precession of gyroscope, and we can find the angular speed of that precession. So after that dl, we have a new L plus dl, angular momentum. So from all that theory, if we denote that angle d phi, we can find angular speed of precession of gyroscope. That is omega. In your books, it would be rotation of gyroscope wheel would be omega, and that is omega p. No, I used omega capital to distinguish more. So that omega, we remember what is angular velocity? Change of angle per unit of time, right? So that would be d phi over dt, that particular d phi over dt. Now, if you think that dl, it is a small arc which correspond to angle d phi, subtended by angle d phi. So that's why that dl can be represented like L d phi, from which we can find d phi is dl divided over L, and substitute the d phi over here into our expression for omega. Then omega, which is angular speed, let me write here, that is angular speed of gyroscope precession, can be determined like 1 over L dl over dt, right? When you substitute that phi, I mean d phi over here instead of the d phi, you will get this. Now and again, now we see a recognizable part of Newton's second law for rotational motion, which tells us that torque acting on the object, no, in general sum of all torques, but here it would be one torque, would be equal dl over dt. So this is torque acting on that wheel. Thus it would be torque over L Now, two more steps needed to find final formula for angular speed of that precession, particularly definition of tau, what it is. So tau, it would be R by W. Then you see R and W, they make 90 degrees. Over here R, over here W, so angle 90 degrees, sine 1. So we just write R by omega. And another part, what is L? L, it is omega, as we agreed, by I. No, I omega usually we wrote, doesn't matter. Let me write I omega better. By analogy with momentum for linear motion. Moment of inertia by omega. And we'll substitute everything here. So we'll have RW divided over I omega. Then also we can write weight of the object like product mg. So it would be mgr and divided over I omega. Thus for angular speed of gyroscope precision, we'll have that it would be mgr and divided over I omega. Let's write scalar quantity. So direction would be determined by direction of change of phi. So phi in this direction. So we have again a right hand rule we can apply and determine direction of omega. So to write in vector form, you can write here small unit vector and write in that form as well. Now, because that effect is very non-intuitive, let's write a small part of the film where would be represented well some experiments with gyroscopes, and then we'll go back to that theory so we can analyze more. That is part of lecture from MIT. Let's see if I can get any sound here. But at least we can hear the sound here. There is no sound. Work though, something is not connected. Sometimes you don't put the speakers. Okay, you can watch experiment though itself. Here you can see Let me switch on screen. Here you can see theory of that effect. So whenever you have, for example, wheel and it is not rotating, if you give a certain torque, you see two forces applied to that wheel. Here, certain axle on which that wheel is located. So if you apply that force, it will just rotate like that, right? But if it is in rotation, with that action, applying those forces, so acting with the torque, you will change angular momentum of the wheel due to the action of the torque. So instead of this position, we'll have different position of the torque, so that wheel would be tilted. So let's see how. Maybe someone knows more like about computers, what would cause it? There is no sound here. Who knows computers well? Okay, so
after I have stopped, the angular momentum of the system as a whole can no longer change because there's no torque on the system. The only way that nature now can solve that problem is to tilt this wheel in the way I have indicated here and to make it spin in this direction, and it will stand still. In other words, I hold it in my hand, the wheel, I will get it, I give it a spin, I hold it in my hand, I spin it towards you, and I'm going to put my right hand towards you and my left hand away from you. The spin angular momentum is now in this direction. So I'm going to give it a torque like so, that means what? And what will the wheel do? The wheel will do this. Very nice. Watch it do. That's good. Like this. Again. I'm going to torque by pushing my hand towards you. And the wheel does something completely unexpected. Simply tilts. If I torque the other way around, then the torque, of course, will make it split like this. I'll give it a little bit more. Spin angular momentum. So now I move my left hand towards you, and my right hand towards me, and then I expect that the wheel will do this. That's what it does. Extremely non-intuitive. These torques applied to a spinning wheel always do something that you don't expect. However, there's one thing that always helps me in terms of guiding me, and that is you can always predict that the spin angular momentum will always move in the direction of the torque. This is external torque I apply. Let's go over that again. We have here the spin angular momentum that you saw pointing in this direction, and I apply the torque in this direction, vector. And what does the spin angular momentum do? It goes in the direction of the torque. And then when I stop with that torque, then of course nothing changes anymore. And so what happens is this wheel tilts. Notice that L, spin angular momentum, has moved from here to here. And I was torquing in this direction. So it moves towards the torque. If you have digested this, then you can test yourself now. Now we have the same wheel. I'm going to rotate it in exactly the same direction. But now I'm not going to torque like this, in the Z direction, or like this, in the minus Z direction. Now I'm going to do this, or I'm going to do this. Try now to really concentrate on what I just taught you. Try to give an answer to the following question. The wheel is rotating. I hold it in my hand, and I'm going to torque it like this, so that the torque vector is in due direction. Angular momentum was like this. Torque is like this. What will the angular momentum vector do? Move in the direction of the torque. What will the spin angular momentum vector then do? If the torque is in this direction, going to spin this wheel. I'm going to spin it with a high angular momentum, high spin angular momentum. And then when I stop with my torque,
A little bit going back here, because really how he says is very unintuitive. So do you see how torque goes upward? Because you apply two forces, each of them makes that object to rotate in this direction. Like if you look from top, it would be a counterclockwise direction. So always in the direction of rotation for fingers. So some goes up, you see torque upward. Due could be one force, here two forces, goes upward. So as was said in that field, angular momentum, which is L before, when it rotates, again also right hand rule, so angular momentum in this direction. So increase of L, change of L, always in the direction of torque. That should be remembered. So you see that line delta L exactly in the direction of tau. I have some kind of pointer. So our delta L increase of that, which causes change basically. It causes basically change of direction of vector L. So that new one would be L plus delta L. So L was here, we added delta L and got a new position. So L always would be perpendicular to plane of that rotating wheel. And that's why that wheel tilt. So particularly it would tilt. So if torque this way, so new angular momentum this way, so that wheel would tilt like that to the left. Okay, so now let's see that experiment when the actual wheel would be suspended, would be located on pivot point, but would be suspended. How it is done here.
we call this motion of the stool.
It gets good angular velocity, as you can see. And now that axle will go
With a
on.
torque exactly as you see on the picture there. You ready? I stop the torque, nothing happens. I torque backwards, I keep torquing. I keep torquing, I feel it in my hand, I really have to push. I keep torquing. And I stop torquing and it stops. The angular momentum vector is chasing, so to speak, the torque. Is that non-intuitive? Very non-intuitive?
Wait a moment, I there is a sound right here.
We call this motion of the stool, and in this case the motion of the spinning wheel, we call that precession.
Let's listen.
So you apply a torque to a spinning wheel, then what you obtain is a precession. I can show you the precession in another way, which is in fact very intriguing. Suppose I have here a string, a rope, like we have there. And I stick into that rope, I attach to the rope this wheel, just like so. And I let it go. Well, we all know what will happen. Come on. Please. All right. Now I'm going to spin it before I let it go. So here at the bottom, at this point P, there's a loop. And here is the axis of rotation of the bicycle wheel, which is solid brass, solid piece. And I give that a length a little r, not to be confused with capital R, which is the radius of the bicycle wheel. So this, capital R. And it can rotate about this here reasonably free. I call that center point Q. And let this be dimensional. Suppose now I give it a spin in this direction, omega s. S stands for spin. In what direction is now the spin angular momentum? Put your hands, your thumbs, spinning in this direction. Yeah? Spinning in this direction, angular momentum is in this direction. That's a spin angular momentum. L spin. Well, there is a force on this system, mg, and that force is in this direction. It has a mass m, bicycle wheel, and it has a radius capital R, and this part is little r. So relative to point P, there is a torque. And the torque is R times mg. This is 90 degrees. So the cross product is nice. Sine of that angle is 1. So the torque relative to point P, R times m times g. In what direction is that torque? R cross F. What direction is that torque? Use your hand, thumbs, whatever you want. You think in this direction? I disagree. R cross F is, you must be kidding. In the blackboard. Not out of the blackboard, it's in the blackboard. R cross F is in the blackboard. There's a torque in this direction. Nature, gravity provides that torque. What will the spin angular momentum do? It's going to move in the direction of the torque. It's going to chase the torque. So what will it do if the angular momentum is here? What will it do? It will do this. And as it moves, the torque will always be perpendicular to the plate, to the string, and R. You can just see that for yourself why that is. At this very moment when angular momentum is like this, the torque is in the blackboard, because it's R cross F. But when I'm here, this R has changed position and always remains perpendicular to the wheel. So the torque will also change direction. And so this angular momentum, spin angular momentum, will keep chasing the torque and starts to rotate freely. That is exactly what I was doing when I was sitting on the stool. Except that I had to apply that torque in my hands like this. It's exactly the same direction. I had to apply it all the time, and when I stopped, the precession stopped. Here, however, the torque will never stop, because this mg will always be there. And I will show that to you, sure. You may say, you must be crazy, because you're violating Newton's second law, F equals ma. This object got to fall. There's only one force on that object. F equals ma, how can it not? The center of mass must fall with acceleration g. Aha. There is not just one force on that object. What do you think is here? Tension in this cable T will be exactly